Chapters 5 and 6, Newton's Laws. We are now finished with the preliminaries and are ready to start the main part of the course. In the real world, no one is given some acceleration and expected to calculate the position by integration. Instead, they are supposed to look at some system and predict its behavior, or start with some desired behavior and design the system to behave as required. The greatest minds of all time did not have the tools to accomplish such tasks until Newton came along and taught us all how to do it. Thankfully, we do not have to invent the tools to systematically solve complex problems. Neither do we have to close our eyes and dream up solutions using our intuition if we happen to have any. We just need to fully understand what Newton told us, and we will be able to start with his laws, use the calculus he invented, and out will pop the beautiful and powerful laws which are the foundation of all engineering and most science. Everyone already knows the famous second law, F equals ma. In this course we will assume that the mass is constant in time. This will be revisited in a later chapter. It seems simple enough, but there is a lot to understand. Of course, you need to be a master of vectors, or you are going into battle unarmed. You should already know everything you need to know about acceleration. What is left is to study force, the thing that causes acceleration. Chapter 5 is just an introduction to Newton's first and second laws and discusses different types of forces. The first law postulates the existence of special frames of reference called the inertial frames. Only in inertial frames an object will move with constant velocity in the absence of any force, and the second law is valid. We will return to this in chapter 19. There are many different forces. Most of the forces we considered are caused by some agent we can see, such as a string, a spring, a table, etc. One force common to many problems is the somewhat mysterious force of gravity. An experiment first done by Galileo. I actually was not there to observe it, but according to the legend, he dropped something off a tower, and in the absence of air resistance, they should fall at the same speed. Of course, right now, the air resistance is much greater on the feather, so it should fall much slower than the marker cap. Now we're going to repeat the experiment, but in a chamber where we removed most of the air. So the air resistance should be much smaller. So now we have a pretty good vacuum. So the only force that should be exerted on these two objects is the force of gravity. They should fall at the same rate. Remember that the force of gravity near the Earth always points towards the Earth. Another common force is the diabolically complicated force of friction, which will merit a lot of attention in the next chapter. We can begin to understand it by doing an experiment. This is just a simple demonstration to show the force of friction. Right now, gravity is pulling straight down. The block is being held up by the board, which exerts a vertical force. If I start to lift this up, a component of gravity is now pulling the block down the plane. Something must be stopping it from going down the plane. There must be a force parallel to the board being exerted on the block. We call that the force of friction. If I keep raising the plane, at a certain point, the friction force can't get any larger, and the block accelerates down the plane. If I flip this over so that we have a rougher surface, then instead of going at about 30 centimeters of height, because the sandpaper is very rough, the coefficient of friction is much larger, and the friction force can get much larger. Its maximum value is mu n, and then it starts sliding down the plane. There are no problems in Chapter 5, but you need to start becoming an expert in determining the forces acting on some object. Chapter 6, the first part. You will find in this chapter that the first step is to determine the forces that act on the body you choose to call the system. Newton tells you that you must choose a body, find the forces that act on that body, and the vector sum of those forces will give you the acceleration of that body, with the mass of that body the constant in Newton's law. You need to practice this crucial step of drawing a free body diagram which shows the body you have chosen and all the forces that act on it. This step, called isolating the body, is crucial in every problem and will often tell you how to proceed to solve the problem. After drawing a free body diagram, you need to practice choosing a convenient coordinate system and then using F equals ma to find the components of the acceleration vector. From that point on, all problems are Chapter 4 problems, which you have already mastered. It is impossible to overemphasize the importance of mastering the process of isolating the body and drawing a free body diagram. Many advanced engineering students feel that this is the most important part of Physics 218.
I'm Tom Locke, Professor of Mechanical Engineering, and this class is a senior level experimentation class where they all have to do experiments. And do you want me to ask the question? Please. What is the most important thing you got out of Physics 218?
Free body diagrams.
There you go. Okay.
Hi, I'm Jim Morgan. This is Civil Engineering 363, Dynamics and Vibrations. Here's my class, and they're going to tell you what's the most important thing that they learned in Physics 218.
Free body diagrams.
Besides doing problems 1, 2, and 3, and exercises 2, 4, and 6, you should look at the figures for all the other problems and exercises in this chapter, and without bothering to read the problem, draw the appropriate free body diagram. There are two possible sins. You can leave off a force which should be there, or you can put a force on the diagram that does not belong. Either sin spells failure. One common type of problem involves blocks on inclined planes. An example is worked out in detail in the text, and this appears again in problem 3 and exercises 4, 7, and 10. These provide practice in isolating bodies, finding components of vectors, and using F equals ma. Newton's third law. For every action, there is an equal and opposite reaction. This is illustrated for simple forces, but it is assumed to be true in general. Second part of Chapter 6. The last part of the chapter involves two elements that appear in many problems. The first is the massless, unstretchable string that often connects two objects. Because it is massless, Newton tells us that the net force on it must be 0, otherwise it would have an infinite acceleration. Of course, real strings are not massless, but this brings in an unnecessary complication at this point. The second element is the frictionless pulley. It is shown in the text that the absence of friction between a string and the pulley results in the tension in the string being the same on both sides of the pulley. In a later chapter, we will consider real pulleys where there is friction. The pulley problems and exercises will test your ability to deal with these two idealized elements. Summary. If you had to memorize one equation, it would be F equals ma. You have to be a master of isolating an object and creating a free body diagram that shows all the forces acting on the object from outside of the body. This enables you to find the components of the acceleration, and from then on, it's just turning the crank to solve many problems. Finally, is there such a thing as too much practice in isolating bodies and drawing free body diagrams? No. Gagum.